yourself because he traveled across the Atlantic. Yeah, through Iceland.
That's right. I traveled through Iceland to get here from Boston. Hi, everyone. My name is Mauricio. I'm here with my peers from MIT, Fabian and Cameron. We're going to share some work that we've been doing on formalizing in natural language to lean using Bayesian inference. So this is joint work with a couple of other people, Catherine Collins, Ramir Patel, Alex, Vikash, Tim, Josh, and Cameron. So broadly speaking, the task that we're going to talk about today is auto-formalization. And this is going to be the challenge of taking a potentially imprecise informal statement and then converting that into a formal language. In particular, we're going to focus on the lean formal language. So ambiguity comes up very naturally in lean. Natural language is inherently underspecified. So there are lots of things that kind of need to be figured out before they're formalized in lean, right? Lean is known for being very pedantic, so lots of details have to be spelled out. So, for instance, if I say the statement, for all x, there exists y such that y squared equals x, it's unclear what type x and y have. And so when an LLM or something formalizes this statement, they have to implicitly fill that hole. Pronoun ambiguity, if a function has a derivative, it's continuous. It's unclear if continuous refers to the function or the derivative of the function. And quantifier scope ambiguity, each f is bounded by some g. It's unclear what the order of those quantifiers should be. If it's for all f, there exists g, or if there exists g for all f. And this is by no means an exhaustive list of ambiguities. These are just, I think, 3 pretty common ones that I've seen. So I think that there are a number of reasons that it's interesting to study auto-formalization. So firstly, this is kind of an interesting way to assess the ability of machines to understand the intents of their users. And if machines can understand the intents of their users better, supposedly these would make for better thought partners. And I think from a cognitive science perspective, it's also interesting to understand how humans alternate between precise thinking and more rough draft type thinking. I think there's a lot of evidence that shows that humans don't think in the sort of statistical way that language models think. It's not really next Logan prediction. There's a lot of rounding that happens, possibly by symbolic means. And so there has to be some sort of interface between connecting these two fast and slow modes of thinking. Defining success for auto-formalization is difficult, however. So traditionally in machine learning, what you might do is you might have a lot of data that has pairs of informal statements followed by a ground truth formal statement. And this is something that is difficult to do in this auto-formalization setting, because for propositions, for instance, any two statements that is true imply each other. And this makes for kind of a vacuous definition of sameness if you choose to use logical equivalence. And for predicates, this is an undecidable problem. In the example that I have below, this is kind of what you might run into if you were trying to use equivalence of predicates for equality checking. The challenge here is that in order to prove that these two predicates are equivalent, you would have to prove basically that all polynomials in the complex numbers have number of verbs equal to the degree, which is a complicated proof. Certainly, it's not one that language models would be capable of proving, or yeah. And despite this, humans still have an intuition for when two statements are equivalent. And it's that sort of intuition that's not really grounded on a precise definition that is kind of the medium between formalization of large math. So I wanted to share a couple quick things about ambiguity before I jump into the rest of my presentation. So I will be playing around a little bit with language models in this talk. So what I wanted to show you is like how does language model like perceive ambiguity in formal language. So here's what I'm going to do. I am going to take a couple statements. I'm going to have a language model output a couple of attempts at formalizing those statements, and then I'm going to use an embedding model to convert that into a vector, and I'm going to reduce the dimensionality so we can see this in 2 dimensions. And that's kind of what that looks like here. So I think there are a couple interesting things to point out. So if I have the statement for all x, there's this y, such that y squared equals x, we run into this thing again where yes, the types are underspecified. But I think it's interesting to note that the sort of embeddings that you get of the language model outputs, they're kind of clustered around the types of the statements. And what I've seen is that they're pretty robust to semantic preserving transformations of the statement, whether that's renaming hypotheses or reordering hypotheses. And for this statement, again, the types end up staying in the same cluster. Another somewhat interesting thing is that the informal statement ends up getting embedded somewhere in the middle of all the formalization attempts. There's something kind of interesting going on here. So this is just repeating what I said. But I take this to mean that language models are really kind of just good statistical predictors, right? So they're good statistical predictors. And so this isn't necessarily a claim that language models are great at formalization or that they're great at detecting ambiguity. I think that there are still a number of problems with this sort of, just take language models and try to formalize. In the past example, so I think that there are some peculiarities if you were to look at the formal statements that are associated with all these points. So firstly, the vast majority of them are not actually well typed. Even the ones that I've labeled, most of them actually will not work at all. A lot of these attempts at disambiguating don't really make a lot of sense. So if I told a human to disambiguate this statement, for all x there's this y squared, you likely would not find yourself saying anything about the natural numbers, right? Because that statement is not true. So as far as language models go, I think they're better as kind of statistical distributions, right? So here's kind of spelling that out a little. Language models are trained on next token prediction. There isn't really a great reason based on first principles that we should expect them to be excellent reasoners. Language models really define conditional distributions for sequences of text. And so here's a diagram that kind of spells it out a little bit more. We really are defining these distributions over what the next token is for a sequence. So here's the outline of this talk. I'll be talking a little bit about auto-formalization as inference, which is this idea that we've been working on. And I'll be showing some preliminary examples and simple case studies. Fabian, the next talk, is going to talk about how we actually implement our system in practice. So I'll be introducing auto-formalization as inference. So inference is this technique in statistics that we're going to use for trying to generate samples from a target distribution that's otherwise difficult to compute. So for instance, a distribution that a person might try to sample from is the distribution that's given by sentences in the English language, conditioned on all words in the sentence cannot contain the letter E. Right, so this is something that's difficult to compute from. The way that ideally one would go about computing this is by just spending their day normally saying the sentences that they otherwise would, and at the end of the day, you take all the sentences that you said and you filter out by the ones that contain the letter E. So all the sentences that you have are kind of organic and they make sense, and they just don't contain the letter E. If you greedily try to sample sentences that do contain the letter E, you'll find yourself in a tight spot most likely the sentences that you generate will be shorter than they should be. And in a lot of cases, they probably just will not make a lot of sense. So this is kind of a challenging problem, but there's a lot of work that has gone into posterior inference, which is kind of what we're trying to leverage in this project. So one of the big ideas here is trying to use language models more as the distributions that they're really intended to model. We're going to try to use language models as a proposal distribution for sampling from this target. But what might a target distribution for this look like, right? So here's one suggestion for how you might frame this as a posterior inference problem. You might say that probability of a formal statement given an informal statement is proportional to the likelihood that a language model gives to the formal statement given the informal statement, and then the informal statement given the formal statement, and multiply that by a restriction that says that the statements all have to be well typed, multiplied by a possibility check. So this is a difficult distribution to sample from, but we can try to sample approximately. And Bobby's going to talk a little bit about that. So I'm going to explain a little bit what all these terms mean, but it's just a big product. These first two terms are supposed to encode cycle consistency. Okay, so this is saying that the informal statement that you get how you informalize the formal statement, that should ideally be pretty close to the original statement that you came up with, right? So the first statement, the likelihood of the formal given the informal, that's pretty intuitive. And then the reverse direction is going to try to keep things consistent, right? And that kind of is what this diagram is showing. It's saying that if you formalize and then you informalize, ideally this loop will kind of stay the same. The probabilities here that we're going to get for these two directions are going to be assigned by a language model. The prompts are going to be something like, in the forward direction, formalize the statement, and the reverse direction is going to say, state this statement in natural language. And then for the two continuations that we're going to get, we're going to score those using the likelihood of the language model. So here's a case study. Let's say that you wanted to formalize the statement, if f is continuous on a closed interval, then it is bounded. There are a lot of ambiguities here. Firstly, it's unclear what lean libraries I should use. It's unclear what the domain of the interval is, what the domain of f is, what the quantifiers of the interval and f are, what the quantifiers are, the interval. The statement is also false, right? The correct statement would be that if f is continuous on a closed and bounded interval, then it's bounded. People seem to have a pretty strong preference toward formalizing statements that are true. So ideally some auto-formalization system would up-bias formalizations that kind of salvage the correctness of the statement. Natural language is inherently underspecified, so these sorts of questions need to be figured out. Okay, so what I'm going to go through here is on the right-hand side, I have the log likelihood of this formal statement. Okay, the log likelihoods here are going to be assigned by an LLM. The left, this middle column is the log likelihood of the formal statement given the informal statement, so kind of the forward direction, and this column is going to have the informal statement given the formal statement, like the likelihood of the informal given the formal. What we do in our target distribution, right, if you recall, we take the product of these two likelihoods, and that ends up being the same as if I take the sum of the log likelihoods. Okay, so here's an example of an attempt at formalizing the statement. For all f, for all a b, a less than b, f is continuous on this closed set. There exists m such that for all x, So the language models give pretty good predictions here. This is a pretty good formalization. It's pretty faithful to the intent. It does fine. Here's another attempt at formalizing the statement. The forward and the reverse directions are both lower than the original one, but maybe not terrible. What this is saying is that if you have f that's continuous on all of the numbers, then for all a and b, f is bounded on b set a and b, right? So this is kind of saying something stronger than the version above, because I require here that f is continuous on all of the units. So here, there's this weird existential quantifier that comes in, and that's reflected in both of these likelihoods being lower than the original, right? These are bigger negative numbers. That means that they're lower likelihood. Here's another attempt. So this uses the predicate is compact, which is actually different from the original again, and these again are assigned lower likelihoods. But here's something else that's reasonable. For all f, for all AB, now we use this predicate bounded on f, and this ends up being a lower or a higher log likelihood if you take the sum of the the forward and the reverse directions. Okay, so my reading of this, the way that the reason that I think this makes sense, because if you go back here, right, in the reverse direction, right, the informalization direction, if you were to informalize this first statement, right, the way that you would probably go about that is by spelling out this bound m, right, which this statement at the top does not do, right? It just says is bounded, and that seems to me to be more this shape of this statement right here, where you say that f is bounded on AB. Right. So this is kind of an example of the reverse direction behaving the way that you expect. Right. So cycloconsistency is in some way doing a better job of preserving the original intent for this statement right here. And then here's another way of formalizing this statement. This one's also not very good, and that's reflecting lower log likelihoods. Okay, so that was cycloconsistency. No, back for a second. So this is kind of broadly a trend that I've seen with some other attempts at formalizing statements. These log likelihoods seem to have a pretty good signal of whether or not you're on the right track or not, whether or not a formalization really is faithful to the informal version. So I think that there's a good signal to be drawn out of these log likelihoods. Okay. So next, you might restrict that the outputs that you get from your language model are well typed, right? And if you were to do that, you would observe this predicate BDD dot above, BDD dot below hallucinated. And this is a thing that happens pretty often when you tell a language model to output lean. And in fact, all of these things were actually hallucinated. And at the end, there's only actually one thing that works, right? So this well typedness check is pretty strong. It eliminates a lot of garbage. And then finally, there's a plausibility check that you could incorporate into this potential or this target distribution. And this is an attempt to encode a bias that people have when they formalize statements. It's one of many biases that I think that you'll agree that people have when they try to formalize statements. So firstly, I might have a bias toward formalizing correct statements, right? Correct statements are more likely what was intended. Statements that are falsifiable via a counterexample are less likely to be what was intended. Statements that cohere with earlier context are more likely to be what was intended. Non-trivial statements are more likely to be what was intended. And statements that match with statements stored in my memory are more likely to be what was intended. So these are, I think, are biases that people have when they're formalizing statements. Okay. So I think that a common thing that happens when you're reading a math textbook or a paper is you find a statement and you are unsure what the author meant by a sentence, right? And you say, can I try to figure out which of these two paths to go down by trying to come up with a counterexample for the wrong one? So if I see the sentence, every positive number has a square root, I might be confused about what the order of these quantifiers should be. If it should be for all x, there is this y such that y squared equals x, or there is this y such that for all x, y squared equals. And one way that you can go about that is by saying, well, 1 and 2 are positive real numbers and they have a different square root. So the correct representation is probably the first version, right, for all x. So the y. Okay, so Lean has the tactic plausible that takes some random numbers and tries to come up with counterexamples to a statement. Okay, so the two examples that I have here are saying that for all a is greater than or equal to 0. So it's unclear what the type of a is. So if I try to formalize by saying that a is an integer, then plausible would easily come up with a counterexample. So in the case here, plausible found a equals -1 causes the statement to not hold. Whereas if I said that a was a natural number, then plausible doesn't throw any errors. Notably, it doesn't actually prove the statement. It just says that I couldn't find any counterexamples, right? And that's why there's this yellow underline. It's saying that plausible is kind of temporarily filling in this statement with an instance sorry that's nested somewhere. Plausible. Right, so unable to find a counterexample when a is an okay, and so here's something that you get. So possibly you're formalizing a statement and you're a language model and you generate 4 things and you're able to eliminate some things that are unreasonable. Okay, so I might eliminate here again the instance where I set a to be an integer. And then here's something else that comes up pretty often in the kind of AI theorem programming data sets out there. There are a lot of data sets for language model theorem proving that formal statements are actually wrong. And a common cause for this wrongness is issues like this, where Lean functions try to be total, so they throw out junk values for types that are kind of bad. So for subtraction, if I have a subtraction of 2 natural numbers, then that's really going to be a bonus. So it's going to throw out a 0 instead of a negative number. And plausible is going to be able to catch that because it'll plug in some numbers and it'll see I got a 0 instead of the negative version. So this has to be wrong. Right, so this is not going to be a problem for other ways for other data types for X, Y, and Z. Okay, so I've talked a little bit about these 3 different components to the to a target distribution that you could try to target. But this is also a really extensible framework that we have. You could have another product for a soft weighting that has a preference for statements that are provable with a hammer. So instead of weighting this with a binary signal, you could either strongly upweight statements that are provable with the hammer while not downweighting statements that are not provable with this hammer. You can have a binary signal that has a preference for the formal statement being non-trivial. You can have a preference for formal statements that cohere with the surrounding context. And I think that these things would, in general, all make auto-formalization perform a little bit better. Okay, so that's the end of my talk. To repeat, I said a little bit about auto-formalization's inference and then showed you some preliminary case studies and experiments. Fabian next is going to talk about useful signals and constraints for auto-formalization and implementing our algorithm inference. So yeah, thank you all. Yep.
Hi. This question is about the plausibility factor.
Yeah.
So the idea is disambiguation is done based on how much confidence we have on the statement that it's a true statement. Right. That's what the plausibility factor is supposed to encode.
Right. It's a bias that you might have toward correct statements.
Correct. So if I so for a statement which has kind of two possible formalizations, one of which is not true, then for that the plausibility factor would be less.
So I guess what I had in mind with the plausibility factor is that you would use this in cases where you knew that the statement was true. If you were in a setting where you were looking at statements that have some possibility of being true or false, you might not incorporate this into your target distribution.
It makes sense because, for example, if you formalize proofs, you have like proofs by contradiction where you just like you get to a false statement and you say, oh, this is a contradiction. That's why. So in that case, like we just don't want true statements. We want like this. We want the formalization to mean exactly what's in the text instead of it being a true statement.
Yeah, I think that definitely makes a lot of sense. That makes a lot of sense. Yeah, thank you.
Some more questions?
Back to the slide where you have the embedding for X of type CN.
Or sorry,
This was somewhere in the beginning.
at the beginning. Okay. It's very light. Yeah. This slide.
So we got interface embedding.
Oh yeah.
So what does this actually show? You have a number of training examples with the word X and then different embeddings for X.
So each of these points is associated with a formal statement, right? And I can get an embedding for each of those formal statements and then reduce the dimensionality to 2.
This is for the whole
statement, right? Yeah, not just
X.
So the highlighting that I've done here is saying that the X inside of the formalized statement was interpreted to be a real number or an integer.
Okay. And that was done by hand?
That was by hand, yeah.
What were the clusters in the right side picture?
Sorry?
The clusters on that picture look a bit strange. So how they are so big, but how are they obtained?
The clusters?
Yes.
Also kind of visually,
Because visually you would see some different clusters.
no, I agree. The distinction that I want to make, okay, maybe clustering isn't the best word here, except I think it kind of is in this example. But there's definitely a line that you could draw here, and you could say everything to the left-hand side is real, everything to the right-hand side is an integer. So I think that there is something that's kind of being preserved here by the language model, but I think this goes to what I was saying about. I don't think that it necessarily makes sense to say this is an end-all be-all solution. There's, I think, some statistical quantities that are being preserved by the language model here, but it's at the end of the day, it's not really doing a great job of formalizing the statements.
Okay, so how do you represent let's say the under specification with the possible distributions of the quantifiers in a formal way, not in the natural language. Because in the natural language you have ambiguities, but you have to represent them somehow by some formal language, formally. So instead of having two different formal or logical forms with two different, here we have two quantifiers, but if we have more, then
Yeah, maybe I could say a little bit about kind of this figure right here. So what I would imagine is going on with, you know, for example, in instances where quantifiers are ambiguous, is this distribution of lean statements that a language model comes up with is probably something that's kind of bimodal, right? So where you have one mode that is quantifiers that are of one order, and in the other mode you have quantifiers that are of the other order, and right. So you know, the rest of our target distribution would end up eliminating things that are not well typed, and there are probably a couple of statements in here that aren't really plausible, so you would eliminate those. And in the end, I think you would get something that's pretty sensible.
it's an ordering of the possibility of that order is there.
What do you mean by ordering?
So we still have to formalize. We have to get to a formal language
Yes.
to represent a sentence with two quantifiers, fixed quantifiers. So, which means that in the standard way, you end up with a formal language which represents the order of the quantifiers. So, how do we avoid this problem? So Montague, he got it with two different tree structures. And so that's what we have been following by being educated in Montague formulae, but or two different tree structures. But how do you handle that? So the way you are presenting, you are assigning preferences. This is more plausible, and the other is less plausible.
Okay, I see.
You choose one of
Okay.
the more plausible, or the interpreted version,
Yeah.
position.
Yeah.
But a Lean program, it doesn't know which one is
Yeah. Okay. I think I understand.
assign some preference.
Okay,
But
yeah.
imagine that the lower preference
Yeah.
is the one that is actual.
I think that the preference that you would get from these cases of ambiguity and quantifier, the one way that we have gone about this is by assigning preference based on these inductive biases. So right. So for instance, plausible is kind of a heuristic that would allow you to eliminate some of those quantification orders, right? Which is what's done in the next slide, right? So if this is a different way to do it than what it sounds like you're saying, Montague tree. But I think that there is still something powerful here about encoding the inductive biases that people have when formalizing those sorts of statements.
Which means that the bias can represent in some way the context.
Yeah, that's right.
The state of the mind of the interpreter.
That's right.
So two quantifiers is already enough a lot, but four quantifiers is going to be horrible. So
Yeah, possible.
even with a good knowledge, the system still needs to select one of those.
Yeah, yeah, and I think that something that we could do in the near term is maybe take advantage of some of the work that other people have done here for kind of assigning the sort of preferences that you're talking about to quantifiers to our target distribution. I think that would improve it. Yeah.
So actually, it looks to me that I can imagine that with a large language model, you can you can use it as a context and
Yeah, and you're right. And so this is a thing that's extensible, right? So I think that you can incorporate some bias about MLCP trees to this as well.
thank you very much.
Thank you.
See the next talk out. Because it's a continuation. So it's the same topic, we continue now. Welcome. Way to combine different approaches, purely symbolic and probability preferences.